Okay, let's take a look at this polarization problem. I like this one because it's practical and fairly realistic. So in this case, we have a beam of what's being called partially polarized light, and we consider that to be some mixture of polarized and unpolarized light. And I would argue that this is the case we have a lot of the time. It's very difficult to keep light from being polarized. Light can be polarized just by reflecting off of a surface, say. This is why polarized sunglasses are often used by people that work on the water, because that light that's reflected off the surface of the water, that light becomes polarized. So polarization can occur just when light interacts with matter. And so it is often the case that we'll have some mixture of the two. So this question says, suppose we send such a beam through a polarizing filter, then rotate the filter through 360 degrees while keeping it perpendicular to the beam. Okay. If the transmitted intensity varies by a factor of 5 during the rotation, what fraction of the intensity of the original beam is associated with the beam's polarized light? So just think about this conceptually right at the beginning. There's some unpolarized and some polarized. So any change that's occurring in the intensity must only be due to the polarized light in the mixture, right? Because with unpolarized light, when you send it through a filter, what happens? Just you cut off 50% of its intensity right there. Boom. It's just a constant reduction of 50%. Whereas the polarized light, when the filter we're using is aligned with the axis of polarization, it'll all get through. And when the filter we're using here is at 90 degrees or normal to the axis of polarization of the polarized light, then all the polarized light will be gone from our result. So that's where the change is going to occur in when the polarized light is meeting up with the filter. Okay, I say that because that's going to inform how we set up our equations here. So let's let the original beam, right, the original beam be, we're going to use I naught, which is the symbol we routinely use for whatever our original intensity is. So if we say that that is our original light and some fraction of it is polarized, some fraction of it is not. So I'm going to write the equation out this way. I'm going to let F be equal to the polarized fraction, and that's what we're after, right, in this problem. So we're after this F here, um, some polarized fraction of light plus some non-polarized. So that would be, of course, what's left over, which would be 1 minus F times I naught. And I just want to, let's keep track of this. So this here, this is the polarized part of the beam. And this here is going to represent the non-polarized part. And we remember that the variation is going to occur in the polarized part, and the non-polarized part is just going to be reduced by 50%. Okay, now we're going to send the beam through a filter, and now let's write out an equation for the new intensity. I'm going to call the new intensity I prime, right? This is my new intensity here. So what's going to happen? Well, for the polarized part, we know what's going to happen. I've got F I naught multiplied by cosine squared theta, theta being the angle of the polarizing filter with respect to the original light. That it would be how the polarized light responds to the filter, and the non-polarized light responds to the filter in a really simple way, right? It cuts the intensity in half. So we just have to put a 1/2 in front of this term, keeping track of the fact that notice that the non-polarized light has a constant reduction and the polarized light has a variable reduction. Sure, it depends, right? It depends on the angle of the filter with respect to the original angle of original axis of polarization. Okay, so I have that equation. Now, what's cool about this is a cosine function, right? So I know I can, for instance, write out equations for the minimum value. Now, notice that this problem, remember, I'm going to take you back here. They tell us that the intensity varies by a factor of 5. So how can we use this 5? It seems important, right? Well, because this is a cosine function, I can pretty easily express the minimum value of I prime, right? Because the minimum value of cosine squared theta is equal to 0. Yeah, that's just a fairly simple function. So the minimum, then, what that's going to be is just going to be equal to, well, let me write this out just to make it super clear. I naught times 0, right? Plus 1 half 1 minus f I naught. So that leaves me with just the unpolarized light. And you can imagine this. This is the case, right, where the filter is now 90 degrees to the axis of the polarized light. So all the polarized light is gone. That's our minimum intensity. And our maximum intensity occurs when the filter is aligned with the axis of polarization of the polarized light. And the intensity there, or the cosine, the maximum value of my cosine squared function is equal to 1. Sure. So what does that look like? F I naught times 1. It all gets through. And then we still have this 1 half that is just a constant. It's not changing, of the unpolarized light. Okay, so this gives me, I can simplify this a little bit to be 1 half times 1 plus f I naught. All right, so what we're given in this particular problem, remember, one of the relationships that we're given is that the maximum divided by the minimum intensity is equal to 5, right? That intensity varies by a factor of 5. So what that tells me is that the maximum intensity is 5 times greater than the minimum intensity. That's what we're expressing here. So we can then put that into equation form too, right? I max over I min. So that would give me 1 half 1 plus f times I naught divided by 1 half 1 minus f I naught. That's all equal to 5. This simplifies, of course. 1 plus f divided by 1 minus f is equal to 5. There's a little algebra in there, and you end up with f is equal to 2/3. The written solutions contain the intermediate algebraic steps, but the conceptual pieces of the solution are the most important, of course, and that is figuring out how to use this information that's given to us in the problem. I like it. It's a good, as I said, it's realistic as far as the context goes, the mixture of light, and good critical thinking when you have to figure out how to deal with this factor of 5.